So, in the last lecture you have seen how to find out the solution of integrals using the Laplace transform. Now, let us come to the another application of Laplace transform, how to find out the solution of ordinary differential equation using Laplace transform. In general, what you have observed, to find out the solution of ordinary differential equations, usually you can use the CFPI method or some other methods to find the solution. Let us see what happens here actually. Whenever you have the ordinary differential equation, then the ordinary differential equation can be transformed into one algebraic equation only using Laplace transform, and solution of the algebraic equation will give me the solution of that problem, and from there I can get back the solution of the original problem. So, by this way it becomes very easy. Let us go through that part, that how to find out the solution of ordinary differential equation using the Laplace transform techniques. First, we will do the solution of ODE with the constant coefficients, then we will do the variable coefficients, and then we will see the solution of linear simultaneous ODE. The first one is the solution of ordinary differential equation by the method of Laplace transform. The spelling of method is wrong, it will be METHOD, please note it. This correction we will make afterwards. Solution of linear ODE with constant coefficients, we will do it. What is the type of linear ODE with constant coefficient? You consider this differential equation, linear differential equation with constant coefficients C 1, C 2 like this way, C n. I have written the general form d n y d t n plus C 1 d n minus y d t n minus 1 like this way, C n minus 1 into d y by d t plus C n y equals f t, where f is a function of the only independent variable t. Here y is the dependent variable and t is the independent variable. So, f t is a function of the independent variable t. So, this is a linear differential ordinary differential equation of the form d n y d t n plus C 1 d n minus y into d t n minus 1 like this way, C n minus 1 into d y d t plus C n y equals f t. So, whenever you try to find out the solution in normal classical approach, we use the CF and we use the PI. We find out CF, we find out PI, and from there we try to find out the solution of the arbitrary constants using this. So, we are assuming a set of initial or boundary conditions are given, like y 0 equals a naught, y dash 0 equals a 1, y n minus 1 0 equals a n minus 1, where a 0, a 1, a 2, a n minus 1 are the constants. So, effectively if in the earlier one, if you see if I have the power of n, that is d n y d t n is coming, then number of constants should be n minus 1. So, depending upon what is the nature, what is the value of n minus 1 number of constants will be appearing, and this n minus 1 initial or boundary conditions will be appearing. So, that we can find out the values of those coefficients. What we will do? We will take the Laplace transform on both sides of the given equation. Simply we will take Laplace transform of both sides of equation 1, that is ordinary differential equation, use the initial or boundary conditions 2, and using this we will obtain an algebraic equation known as subsidiary equation, and from that subsidiary equation I can find out a solution like in the form y s equals Laplace transform of y t. And once I am getting this, using the inverse Laplace transform, I can find out the value of the equation. Using inverse Laplace transform, the required solution is obtained by finding the inverse Laplace transform of y(s). So, basically the method, if you see, it is very simple. I do not have to think about anything. Whenever the original problem is given to me, I will find out I will take the Laplace transform on both sides of the given equation. I know the Laplace transform of y(n) is what, or Laplace transform of t(y(n) is what, like that, and I will use the initial or boundary conditions whatever is supplied to me, and using those conditions always I can transform my original ordinary differential equation into an equation of the form y(s) equals Laplace transform of y(t). That is, Laplace transform of y(t) equals some function of s. So, that from there, if I take the inverse Laplace transform, then I have to find out I can find out the value of y(t). Please note one thing over here. All the values of the conditions are given at the point t equals 0. That is, y0 equals a0, y0 0 equals a1, like that way. Because if you take any value of the function at any other point, I have to use some other substitution, because whenever I take Laplace transform, always it is taking at the point t0. If I take the second derivative, there also first derivative value will come in terms of t0. So, let us see how it works. I want to solve this problem d2y square d2y dt square plus y equals 0. I am taking a simple problem at first. With y equals 1, dy dt equals 0 is given when t equals 0. Let us see the solution process. So, effectively your problem is d2y dt square plus y equals 0, and it is given to you y equals 1 and dy dt equals 0 when t equals 0. This is given to us. So, what I will do? I will take Laplace transform on both sides of the given equation. First equation I have taken as a constant on the right hand side of the given ODE. Afterwards, I will take a function of t on the right hand side. Like this way, we will solve various type of problems. So, Laplace transform of y double dash plus Laplace transform of y, this is equals 0, taking Laplace transform on both sides. Now, using the properties of Laplace transform, I know what is the Laplace transform of y dash. Laplace transform of y double dash is s square into Laplace transform of y minus s into y 0 minus y dash 0. This I know it from formula. The value is for, this is for Laplace transform of y double dash. From the definition, we have done it earlier. Laplace transform of y double dash is s square Laplace transform of y minus s y naught minus y dash 0 plus Laplace transform of y. This is equals to 0. Now, y 0 you know, y 0 is 1 from here, and also y dash 0 is 0 here, because y is 1 at t equals 0, dy dt is 0 at t equals 0. So, substitute these values on this equation, so that I can write down s square into Laplace transform of y minus s into 1 minus y dash 0 is 0 plus Laplace transform of y. This is equals 0. So, you see, from here you can write down Laplace transform of y, s will go on that side. So, s by this will be s square plus 1. So, we got the form Laplace transform of f t equals or y t equals y s, or Laplace transform of y equals some function of s. Once I am obtaining this, so I can write down from here, I can write down y equals Laplace inverse of s by s square plus 1. Laplace inverse of s by s square plus 1, and I know what is the Laplace inverse of s by s plus 1, that is the function whose Laplace transform is s by s plus 1, that is cos t. So, I obtain the solution as y equals cos t. So, you see in very small steps without doing much calculations, I am transforming, I am taking the Laplace transform on both sides of the given equation, and by that way the ordinary differential equation is transformed into an algebraic equation like this. This is the algebraic equation. Here I am substituting the values which are provided to me, that is initial conditions or boundary conditions, whatever it may be. Using those values I am getting a form like this: Laplace transform of y equals s by s square plus 1. So, that you can write down y equals Laplace inverse of s by s square plus 1. So, that y is equals to nothing but cos t. So, I hope it is clear that whenever I have the ODE, I am taken only now at present I have taken ODE with the constant coefficients only, not variable coefficients. So, once I am doing it, I am just putting it, then I will obtain one algebraic equation of the form of Laplace transform of y equals some function of s, and from there I can find out y equals Laplace inverse of s, and by evaluating Laplace inverse of the function of s, I can obtain the solution, that is y equals some function of t. So, this is the basic mechanism what we use over here. So, just here I have taken this, I am finding out the solution over here, and I am finding Laplace transform of y equals s by s plus 1. So, that I can obtain y equals cos t as the solution. Next, another problem: solve d 2y dt square minus twice dy dt plus 2y equals 0 with y equals 1, dy dt equals 1 at t equals 0. So, I will take Laplace transform on both sides of the given ordinary differential equation. I will obtain Laplace transform of y double dash minus twice into Laplace transform of y dash plus 2 into Laplace transform of y equals 0. So, I am just writing that thing only. From there, taking Laplace transform on both sides of the given equation, Laplace transform of y double dash equals Laplace transform of y double dash minus twice L Laplace transform of y dash plus twice L Laplace transform of y, this is equals 0. Again Laplace transform of y double dash, this I can write it as s square into Laplace transform of y minus s into y 0 minus y dash 0 plus 2 into, sorry, not plus, it will be, this will not be plus, minus is there, minus 2 into Laplace transform of y dash, we know it, s into Laplace transform of y minus y 0. So, I am writing this s into Laplace transform of y minus y 0, I am obtaining this, I am getting this one, and plus twice Laplace transform of y, this is equals to 0. So, what I am getting? S square Laplace transform of y minus s y 0 minus y dash 0. This term is for this one, this is for Laplace transform of y double dash. This term whatever I have written, this particular term, this term is for this term, and this is twice L Laplace transform of y. Now, I know the value of y 0, y dash 0, all these values. So, if I substitute this, I will obtain s square into Laplace transform of y minus s minus 1 minus 2 into s into Laplace transform of y minus 1, y 0 is 1 plus twice Laplace transform of y, this is equals to 0. I am obtaining this because y equals 1 and dy dx equals 1 at t equals 0. So, if I simplify this, I can obtain Laplace transform of y in terms of a function of s only. This you will see you are obtaining as s minus 1 by s square minus twice s plus 2. So, I got this equation Laplace transform of y equals s minus 1 by s square minus twice s plus 2. So, that you can write down y equals Laplace inverse of s minus 1 by s square minus twice s plus 2. So, once I am getting this one I can write it in the form of this is equals again I can write down Laplace inverse of s minus 1 divided by s minus 1 whole square plus 1. Please note this thing. This is Laplace inverse of s minus 1 by s minus 1 whole square plus 1. So, that this y. So, what you are getting, let me write down clearly on the next page, y equals you are obtaining Laplace inverse of s minus 1 divided by s minus 1 whole square plus 1. So, now Laplace inverse of this is given, this s minus 1 is there, this s minus 1 can be replaced by s by the shifting operator theorem. So, this equals you can write down your y equals e power t into Laplace inverse of s by s square plus 1. E power t, this operator is coming over here because s minus a is here. So, a value if I put e power t into Laplace inverse of s by s square plus 1. Here I am using the property of inverse Laplace transform in this case. Please note this thing. I am using this one and you know the value of this Laplace inverse of s by s square plus 1, which is nothing but the cos t. So, I obtain the solution as y equals e power t into cos t, which is I am getting by evaluating Laplace inverse of s by s square plus 1. So, by this way I can find out the solution. Let us see the same thing I can show it like this way. I am taking the Laplace transform on both sides, I am obtaining this. From here I am putting the given conditions y equals 1, dy dt equals 1 at t equals 0. By substituting these values y 0 and y dash 0, I am getting this. So, now I am getting Laplace transform of y equals s minus 1 by s square minus twice s plus 2. So, that y is Laplace inverse of this. So, using the first shifting property as I was telling, I can write it as e power t into Laplace inverse of s by s square plus 1, and from here this is I am getting the solution as e power t into cos t. I am obtaining the solution. Now, in the earlier problem if you see the right hand side you had the value 0. Now, I am taking another function where I am writing d2y dt square plus y equals t cos t 2t with y equals 0, dy dt equals 0 at t equals 0. Means now it is a function right hand side you have a function of t f of t which is t cos t. So, I have to evaluate. See, first part what we did, if there is only 0 on the right hand side of given ODE. Now, we are solving the problem where on the right hand side of the ODE we are having a function of t also. So, your equation is d2y dt square plus y equals t cos 2t. You take the Laplace transform on both sides of the given equation. So, Laplace transform of y double dash plus Laplace transform of y, this is equals Laplace transform of t cos 2t. Taking Laplace transform, this now you know, you are familiar, Laplace transform of y double dash is s square into Laplace transform of y minus s y 0 minus y dash 0 plus Laplace transform of y. Now, this Laplace transform of t cos 2t, this again using the property, I can say this is nothing but minus dds of Laplace transform of cos 2t. This one I can write it as using the property minus, since t cos 2t is there. So, minus d ds into Laplace transform of cos 2t, this we can write down. Now, on the left hand side substitute the values of y naught and y dash 0, y 0 and y dash 0, which is given to us. Y is 0, dy dt is 0, means y dash y 0 is 0 and y dash 0 is also 0, which is given to us. If I substitute these two, then I will obtain s square plus 1 into Laplace transform of y. This is equals minus d ds of Laplace transform of cos 2t is known to us, that is s by s square plus 4. So, that if I just differentiate once, I will obtain the value. So, let me see Laplace transform of y. This is equals minus 1 by s square plus 4 plus 2 s square by s square plus 4 whole square. I will obtain this 2 s square plus s square plus 4 whole square. So, now Laplace transform of y, you can write it very easily. Laplace transform of y, this is equals s square minus 4 by s square plus 1 into s square plus 4 whole square. I am getting this. So, Laplace transform of y you are getting by simple calculation, algebraic calculation, you are obtaining s square minus 4 by s square plus 1 into s square plus 4. So, now I have to break it in such a way that in the denominator you have only one factor. Using the normal procedure, I am just writing at one go that Laplace transform of y, this after breaking you will obtain minus 5 by 9 into s square plus 1 plus 5 by 9 into s square plus 4 plus 8 by 3 into s square plus 4 whole square. So, once I am getting this individual 3 terms with only one factor on the denominator and whose inverse Laplace transform is known to me. So, now I can write down y equals minus 5 by 9 Laplace inverse of 1 by s square plus 1 plus 5 by 18 it will come Laplace inverse of 2 by s square plus 4 and this will be plus 8 by 3 Laplace inverse of 1 by s square plus 4 whole square. So, y equals minus 5 by 9 1 by s square plus 1, that is it will be sin t plus 5 by 18 2 by s square plus 4, that is a by s square plus a square. So, that it will be 2 into y 2 will come, this will be only sin 2 t 5 by 18 into sin 2 t plus you are having this thing 8 by 3 into Laplace inverse of 1 by s square plus 4 whole square. So, now I have to find out the Laplace inverse of this, for which I cannot find it or I cannot tell what is the Laplace inverse of this directly. But I think we have solved this type of problem earlier. I hope using convolution we can find out the solution very easily. So, now we will find out the Laplace inverse of this at first. Let us see this one, Laplace inverse of 1 by s square plus 4 whole square, 1 by s square plus 4 whole square. This I can write it as Laplace inverse of s square plus 4 into Laplace inverse of s square plus 4. I know 1 by s square plus 4 is the Laplace transform of the function sin 2x. So, we have two functions Laplace inverse of f into g, and this I can write down in the form of this is f star g. So, this I can write it using convolution that half into sin 2x into half into sin 2 into t minus x dx. And we know Laplace inverse of 1 by s square plus 1 is half into sin 2 t. So, this I am writing in terms of integrals 0 to t. This is basically Laplace inverse of this is f star g, where f is this function sin 2 x half sin 2 x and g is half sin 2 t. So, using convolution definition I am writing it as 0 to t half sin 2 x into half 2 into t minus x dx. So, this equals, you can write down 0 to t, this sin a sin b if formula if you use, you can write it as cos 2 into t minus 2 x minus cos 2 t into dt. And I can find out the value of this, evaluate the integral easily. So, that I will obtain minus 1 by 4 sin into 2 into t minus 2 x minus this will be x into cos 2 t, and the limit is from 0 to t. If I evaluate the limit, I will obtain this equals 1 by 16 sin 2 t minus t by 8 cos 2 t. So, ultimately Laplace inverse of 1 by s square plus 4 using the properties of convolution, I am evaluating it like this, and again it is a simple form, and I am getting the value as 1 by 16 sin 2 t minus t by 8 into cos 2 t. So, that now I can tell the value of y as y equals minus 5 by 9 sin t plus 4 by 9 sin 2 t minus t by 3 cos 2 t. Substituting that value and simple manipulations, the value of the solution of the given ordinary differential equation will be this. So, these are the solution process whenever you are using the variables with constant coefficients, ordinary differential equation with constant coefficients. In the next lecture also, we will continue with the solution of some other type of ordinary differential equations.